Okay, this problem highlights Newton's second law of rotation and calculating torques. So I would consider our key steps to be, so step 1 is going to be calculate the torque from the what's called a pulling force, or the just a force that's exerted on the cylinder, and the torque, or a torque that's created by gravity on the cylinder. So that's going to be step 1 of dealing with this problem. Okay, and then step 2 of solving the problem is going to be use Newton's second law of rotation. We'll say in rotational form, because we know that Newton's second law in translational form is F equals ma, but in rotational form it looks a little bit different. Not much, but a little bit different. Okay, but I'm getting ahead of myself. Let's read the problem here. We have a cylinder with rotational mass, standard for a cylinder, of 1/2 mr squared. Rotational mass is just another way of saying moment of inertia. We're given the mass of the cylinder, and we are given its radius. We're told that it is standing vertically on a flat frictionless floor, and a force F is exerted at the center of the cylinder, as shown. So the cylinder will climb a step against which it rests. Okay? So you can kind of imagine that cylinder is going to push off of the corner of the step. And that's important. The step has a height of 0.14 meters, or 14 centimeters. And the question asks, what is the value of the applied force, F, that is necessary so that the cylinder pivots about the edge of the step? Okay, that's great, great phrasing there, because it tells us where to put our pivot point, with an angular acceleration of 20 radians per second squared. So not only do we want the cylinder to roll up the step, but we want it to roll up and speed up. Okay, and so that will allow us to plug in our known values and solve the system. Okay, so we want to go to the figure here and clearly label our pivot point. Okay, so this right here is our pivot. All right. Pivot point. All right, so that means that we're going to have a moment arm for our forces, because we're showing one of the forces, the force of friction, the force of pulling, or whatever, just the applied force, but they're not clearly showing the force of gravity, so I'll add that. Now the force of gravity acts at the center of mass. Well, the center of mass is at the center, because it's a uniform cylinder. Okay, and yeah, it's not exactly stated, but it wouldn't have that moment of inertia otherwise. And unless otherwise stated, we can basically assume that or can actually carefully assume that the gravity will act at the geometric center, because that will match up with the center of mass. Okay, so then let's draw a vector that represents the force of gravity. All right, so this right here is Fg. So those are our two forces. Each of those forces are going to create a torque. They're going to create a torque relative to our pivot point, which is not the center, nor is it the contact point with the ground, which would be kind of right here, which would be typical for rolling motion. No, this is rolling up a step, which is different. So the distance that we care about is going to be this distance here. All right, so let me draw it in black. So that right there is our axis of rotation. So I'm going to call that R. All right, so what we need to find then is the component of our force, our external force, and the component of the gravitational force that's perpendicular to R. All right, or in other words, we just have to think about the definition of torque being force, the moment arm, and sine of the angle between the two. Okay, so we can see that there's definitely a little bit of careful consideration that goes into correctly calculating the torques for both forces. All right, so let's start with the torque done by the force. All right, the unnamed force, the pulling force. Okay, so that is going to be F, okay, and then times R, and times sine of the angle between R and F. Okay? And that angle is this one right here. All right, this is phi. Let me draw it there. All right, so that's phi. All right, meanwhile, for the torque of gravity, we'll have mg, all right, or big M, g, times r, times sine of the angle between the gravitational force and the axis of rotation, r, right? Okay? Now notice I keep calling it the axis of rotation because really the moment arm is this thing here. It's the component of the axis of rotation that's perpendicular to the force, okay? Or this, or we'll have a different, moment arm here once we put the correct angle in there. And so, right here. So that's the moment arm, and whereas r is the axis of rotation. It's always the same, okay? Because it's just relative from the center of mass to the pivot point. Okay, but as I've been hinting at here a little bit, is that it's not going to be the same angle, okay? So the angle has to be, well, if you look at the figure, it has to be this angle, and we're going to call that one phi. All right, so we see that they're different angles. Why? Well, because they point differently relative to that axis of rotation. And so, and why does that make sense? Well, we know we get maximum force, or rather maximum torque for a given force, when the angle between the axis of rotation and the force is 90 degrees. So in other words, if the pivot point was down here at the ground, then this force would have 90 degrees and it would be creating maximum torque. So we can see then that phi could grow to 90 degrees, and that would create maximum torque. Likewise, the force of gravity would create maximum torque if the pivot point was up here. Say if the step was high enough that it got all the way up to the the height of, or 1/2 the height of the cylinder, or the diameter of the cylinder. All right, so that's how those forces would create maximum torque. So we can then kind of think about the angle, and as the angle grows, and ultimately it's just the direction between the vectors, or just the angle between the vectors, right? Okay. So how do we actually calculate those angles? Well, we gotta make some right triangles. So what I'm going to do here is I'm going to draw what quantities we know. Okay. So we know we've got our cylinder. Okay, and then we have some step, like so. Okay, and we have, okay, so now let's make a triangle. So we know that this here is equal to r, right? So the distance from the center to the contact point with the ground. And then we know that this one's also equal to r. Okay. So then what we want to do is we want to, make a right triangle. Okay, so we got this height here is h. All right. And that means that this height is r minus h. Okay. So then, if I look at this right triangle, this one right here. Okay. So that is going to be how I'm going to find phi. Okay. And then in order to find this one here, this other angle, in order to find theta, right? So this one here is going to be our phi. Okay. Let me blow this whole thing up. It's a little small. All right. And so then if I want to find theta, then I need to consider it's just going to be 90 minus phi. So we're in good shape. So once we find phi, we can easily find theta, but I'll label it on the figure as well. All right, so there's our theta. Okay, so let me write it out. So in order to find phi, we'll use sine. So sine of phi is going to be opposite over adjacent, or r minus h over r. Okay. Make sure I did my geometry correct there. Yes, that side of the triangle definitely has to be R. Yep. And another one is R minus H. So good. Okay. So good. Then we can find phi that way. All right. So then phi is going to be sine inverse of R minus H. Okay. So we have 0.27 meters minus 0.14 meters. All right. Oh, I realized that I have to get this on the page. Okay. So 0.14 meters, and that's all going to be over the 0.27, the radius. Okay. Okay. And we'll go ahead and, oh, actually, I don't know why I'm bothering to find the angle. I mean, I can find the value here. I might as well, since I already wrote it out. But ultimately, it's going to be sine of phi in there, so we might as well just, put this in our expression and not even bother to find the angle. But if we're curious, just to kind of, see the scale of things, all right, so let's just do that over here real fast. We'll do inverse. Let's go to rate or degree mode first. All right. You might be like, well, hold on. In rotational motion, you got to use radians. Yeah, but you can still talk about degrees if you're doing components, right? As long as you're consistent with it. You just have to do radians when you're doing kinematics, because the kinematic equations for rotational motion do only work for radians. All right. So sine inverse of 0.27 minus 0.14, and then divided by 0.14, close off the inverse trig, and we get 68 degrees. All right, so 3 sig figs, so 68.2. All right, great. But like I said, we actually we don't really need that. I mean, I guess it's kind of helpful because we don't have a as clean an expression for expressing phi. I mean, I suppose we certainly could create a right triangle for our or rather for theta. Just thinking about what the right triangle would look like. Right, so we got this one. So basically, right, so we have that right triangle there, which is R. So it's, oh, well, yeah, obviously it's just going to be, it's just cosine because it's going to be adjacent over hypotenuse will be R minus H. So, yeah, so it basically, yes, okay. But I'm just going to stick with the angles in that case, okay? So then we have theta is just going to be 90 minus phi. So we can just do this in the trusty calculator. 90 minus this value here. All right, 21.8 degrees. 21.8 degrees. Okay. Looks good. Looks really good. Okay. Made a mistake. Okay, so it's tangent, obviously. All right, so thank you, listeners, and people watching the video that have been yelling at the screen, being like, it's obviously not sine because it's not opposite over adjacent. It's opposite over, or rather, it's not opposite over hypotenuse. It's opposite over adjacent, which I was writing the whole time, which is the definition of tangent. So let's just, back up and correct that. All right. So let's go here. And basically the red flag for me is the angles just didn't make sense. I thought maybe, oh, well, maybe the figure's not to scale. And I'm like, well, 0.14 is about half of 0.27. So it really shouldn't be 68 degrees. In fact, it should be pretty close to 45, which now we see. So 42.9, all right. And then theta is just going to be 90 minus that. All right, 47.1. Okay. All right, so definitely we can calculate our torques now. I won't show the values in this step; they weren't asked for. So let's move on to step 2 of actually solving for F. Okay, so what does that look like? How do we now use this information about the two torques that we now can calculate? Well, we use Newton's second law in rotational form that tells us that net torque equals I alpha. Okay. So in this case, that's going to be, well, okay, so positive torque is defined as a torque that creates a counterclockwise rotation. Okay, so that means that gravity, the gravitational force, wants to create a counterclockwise rotation relative to this pivot point. It'd want to spin, right? So this force right here would want to spin the ball this way in the counterclockwise direction. Whereas the external force wants to pivot the ball this way in the clockwise direction. So it's going to be tau g minus tau f equals, well, I alpha, which I'll go ahead and put in what we know, which is 1/2 mr squared for I. And we do have a known value of alpha, but we'll just leave it like that for now. Okay. All right. Okay. So then we're nearly there, right? We can really move forward because we want to solve for that f. So let's plug in what we have. So for tau g, we're going to have mgr sine theta, we know what theta is now, minus f r sine phi equals 1/2 mr squared alpha. All right, so now I just want to solve for f. Okay, so that's going to involve adding fr sine phi to both sides. Fr sine phi over here plus fr sine phi over here as well. All right, and then subtracting the 1/2 mr squared alpha from both sides and dividing the r sine phi. Okay, so now f is going to equal mgr sine theta minus 1/2 mr squared alpha, all divided by r sine phi. Okay, so we'll plug in values here. So that means the force that's required is going to be, okay, so we have our 12.7 kilograms. So 12.7 kilograms times 9.8 meters per second squared times 0.27 meters, that was just our radius, times sine of 47.1 degrees. Okay, minus 1/2 times 12.7 kilograms times 0.27 meters squared times our given alpha of 20 radians per second squared. 20 radians per second squared. And then that's all going to be over 0.27 meters times sine of 42.9 degrees. Now, obviously, I could have cleaned this up some more, kind of found some more common terms, like r, for example, simplified the expression, but I'll just plug into the calculator like this. And I mean, it is best to clean it up. You're less likely to make a calculator entry error, but we will just hope for the best. Okay, so 12.7, and then multiplied by 9.8, multiplied by 0.27, times sine of 47.1. All right, unrounded. Okay, minus 0.5 times 12.7 times 0.27 squared times 20. All right, close our parentheses if we did them correctly, because that all should be the numerator. Open parentheses for the denominator. 0.27 times sine of 42.9. Double check. Yep, 42.9. Good. Okay. And close. Okay. So, let's see. Yeah, the expression looks pretty good here. Let's see, can we not? Oh, there we go. Okay, well, we get 83.6 newtons. All right, pretty sizable pulling force, but it was a pretty heavy, heavy cylinder, and we wanted it to not only go up the step, but accelerate significantly while doing so. So we see that we did this by carefully calculating our torques, thinking about our angles, and using Newton's second law. Thank you.